Hello, welcome to Varial Vagupare. In this video, we are going to see about mutarotation of carbohydrates. This particular topic is based on GATE 2025 question. Let us first see the question. A disaccharide X does not show mutarotation in aqueous solution. Acidic hydrolysis of X affords two different monosaccharides. The disaccharide X is. So we see four options of disaccharides are given. And in this particular question, there are two parts. The first part is about mutarotation. They say the disaccharide does not show mutarotation. And the second part is the acid hydrolysis of this disaccharide gives two different monomers. So these two are 2 points based on which we can solve this particular question. This is a very simple question, but then I would want to talk about mutarotation, the different types of carbohydrates, and then what could happen to them when they are hydrolyzed. So let's first see the basics of the disaccharides or carbohydrates in general. There is also a video of fundamentals of carbohydrates. There are two part 1 and part 2 videos on various different types of stereoisomers of carbohydrates and then various properties of carbohydrates. You can look back on our earlier playlist. So now we will see what is mutarotation. Before seeing mutarotation, let us see the basic property of how these carbohydrates are forming cyclic ring systems. So in this particular four options, what we see here is it is a 6-membered ring, and there is also a carbohydrate which is 5-membered ring. So we are now going to see how the cyclization of carbohydrates happen. So this is based on the fundamental reaction between an aldehyde and an alcohol. When we studied aldehyde, we would have studied this under nucleophilic addition reactions. We know aldehydes and ketones undergo nucleophilic addition reaction, and we know that the RO minus and H plus of the alcohol will cleave and will get added to the carbonyl group of the aldehyde or ketone. So we know the carbonyl carbon is positively charged and the oxygen is negatively charged. So the negative group will add to the carbon, and then the polarization of oxygen leads to the addition of the H plus ion. That is how we get this OH and OR. So you have an ether and hydroxy group here. But then we don't call it as an ether, rather we call it as a hemiacetal. So this is a hemiacetal. So in this case, what we see is whether it is an aldehyde or a ketone, when an alcohol is reacted upon by nucleophilic addition reaction, it forms a hemiacetal. If it is a ketone, it will be a hemiketal. So what happens in case of carbohydrates? So we will take glucose molecule as an example. We know glucose is hexose and it is called D-glucose because the OH group from bottom is on the right hand side. That is why it is D-glucose. This is the configuration of glucose, and this is the Fischer's projection as it is written here. And when we see this glucose molecule, we know carbohydrates are polyhydroxy because they are having many OH group, aldehydes or ketones. So glucose is an example of a polyhydroxy aldehyde, and it is having 6 carbons, so it is also called as a hexose. So now we are going to see a similar reaction in this particular molecule. And in this molecule, we know that there are OH groups from the second carbon itself. So due to angle strain, the second OH group cannot react with the carbonyl carbon because we know it will form a 3-membered ring system. So 3-membered rings are highly strained. Then this will become a 4-membered, this will become a 5-membered. And when this OH, that is the OH on the 5th carbon reacts, the ring system will be a 6-membered ring system. And as per Bayer's strain theory, we know 6-membered rings are more stable than the other ring systems. What happens here is the 5th OH group interacts with the carbonyl group in the first carbon. So we know the carbon is positively charged and the oxygen becomes partially negatively charged, and this O cleaves, and there is a negative part to it and then there is a positive part to it. The hydrogen will go to the oxygen, and this oxygen will form a bond with the carbon, and that is what we say in this molecule. So this carbon's oxygen is bonded to the carbon, and what the OH is missing here in this case, Actually, this place an oxygen is missing. So I'll introduce it here. So here, in this case, the O is here and the hydrogen is bonded here. On the other example, you see the OH is on the left hand side. In simple terms, this carbon, which was earlier achiral, has become chiral because now it has 4 different groups attached to it. One is the hydrogen, next one is the OH group, the third is the full chain, and the fourth is the one bonded to oxygen. So this carbon 1, which was earlier achiral, has now become chiral. So whenever we know there is one chiral center, it will have another stereoisomer. So the other stereoisomer is this, wherein the OH is on the left hand side. So this is on the left hand side, this is on the right hand side. So in the open chain, this is a simple way to represent it. But we know whenever there is a cyclic 6-membered ring, and remember, this is not a benzene ring, this is a cyclohexane kind of ring wherein one of the positions is replaced by oxygen atom, because this is the 6th position. 5 carbons and the 6th position is occupied by oxygen molecule, oxygen atom. So when we fix the groups, then we know the groups are accordingly written here. And this representation is called as the Howard's projection, and it represents a pyran ring. That is why this is called as a pyranose molecule. Okay, this structure is called as pyranose. And all carbohydrates, we use the notation OSE. And here, this is called as a pyranose. And because the carbohydrate is glucose, it is also called as glucopyranose. And of course, it is a D-glucose. And now, the newly formed carbon, this stereo center, is has a name, and that is called as a anomeric carbon. Anomeric carbon. And this anomeric carbon is the one which distinguishes between the alpha D glucose and the beta D glucose. All other positions remain the same. So the only difference in configuration will be at this anomeric carbon. And this anomeric carbon results in 2 different stereoisomers. These are called as anomers. And because this is a Howard's representation, the groups attached to the carbon atom are written on up and down time. And so what we see here is, in this particular alpha notation, the OH is below with respect to the second carbon. And in case of the beta notation, the OH is opposite, above or opposite to the second carbon. So this is how you have to remember. So then when you're thinking about writing the structure of glucose, it is very easy. You write a 6-membered ring, and then second carbon, you put it down, and alternatively, all other groups, the bulky groups, are alternate to each other. So in case of alpha D glucose, the OH is also down. And in case of beta D, again, it is in alternate. So in beta D glucose form, all bulky groups are opposite to each other. So that is the most important thing to remember, and you won't go wrong in writing this structure. So these are the 2 different forms of glucose, and they are actually formed because of this intramolecular cyclization reaction. And here, like we saw, there is a OH group and a OR group. So we see here there is a OH group, and this is continuously an OR. That is, R is a carbon chain, right? But then here it is cyclic. So this whole part is OR and a OH group. That is why these two are called as hemiacetals. So glucose form hemiacetal ring, and this is because of this particular reaction of the carbohydrate. So the glucose molecule, which we thought was a single molecule, is not a single molecule, but is a combination of 2 different stereoisomers which have a cyclic structure. So now let us see a similar reaction for a ketone. Like I told you, like aldehydes, the ketones can also undergo similar reaction, and they are called as ketals. So here also you see it is the same thing with respect to a ketone also. So instead of an R group here, you have, H group here, you have an R group. That's the only difference. So in case of fructose, which is a ketone, the ketonic group is in the second carbon atom. So this is the carbonyl group that can undergo cyclization. So cyclization again can result in the formation of 5-membered or a 6-membered ring. And because the 5th carbon is appropriately placed in case of a carbohydrate like a ketone, we see it results in the formation of 5-membered ring system. The 6-membered ring systems are also possible, but they are less favored when compared to the furanose ring system of fructose. Again, what we see here, the same kind of reaction what we noted there. So the OH group is either on the right hand side or on the left hand side. So the accordingly, we will have two different isomers. So in this particular cyclized molecule, we see the first carbon. Please note the first carbon. The first carbon is written outside. You see here the first carbon is written outside. The second carbon is the one which has become a newly formed stereo center. So the second carbon is the newly formed stereo center. Remember, this is the one. So usually there will always be a confusion between the fifth carbon and the second carbon. So when you see the fifth carbon, in case of the fifth carbon, you have a hydrogen and then you have a CH2 group and the oxygen bonded. Hydrogen, the alcoholic group, and then oxygen bonded. Whereas when you see the second carbon, you have the CH2OH. So this is also having CH2OH. This is also having CH2OH. So this is having a CH2OH, and the other side it is having an oxygen. But the only difference between the second and the fifth is the presence of this OH group. So here it is OH, here it is only H. So that is the only difference between the second and the fifth. So you should not get confused here. So when you are writing the structure of fructose, you know the OH groups are again alternate to each other, and there are two sides to the furanose ring. So whichever side you are putting the OH, that will become the second carbon. That is something which you should remember. And this OH can be down or up. Accordingly, we will have the anomeric carbons. So this is the two different anomers of fructose. So now let us see mutarotation. So this is the topic of discussion. So when you see the mutarotation of glucose, as we see, this is the alpha D glucose, this is the beta D glucose. And the beauty about these two stereoisomers or anomers of glucose is they have different melting points. So they are different molecules altogether. So, and they have a specific rotation of plus 112. Alpha D has a specific rotation of plus 112, whereas beta D has a specific rotation of 18.7. So in solid state, you have alpha D glucose and also beta D glucose. But when you dissolve alpha D glucose in water, the alpha D glucose will equilibrate to the open chain structure, and its specific rotation will change from plus 12 to 52.5. The open chain glucose has a specific rotation of 52.5. So if you are making a solution of beta D glucose and you observe its optical rotation, it will change from 18.7 to 52.2. So the slow change in rotation from the alpha D state to the open chain or beta D state to open chain. This is called as mutarotation. So it is a slow change in optical rotation of the carbohydrate when it is dissolved in water. And this slow change is to the equilibrium position or the open chain structure. So this is happening in solution for carbohydrates. So whenever a carbohydrate has this anomeric carbon OH free, or when it is in the form of hemiacetal, then this carbohydrate has the ability to open up into a open chain structure. But then if this OH is blocked or if this OH is converted into some other group, then this particular carbohydrate cannot open to the open chain. So carbohydrates which are monosaccharides can equilibrate between the stereoisomers and the open chain because they have this hemiacetal structure which can open and close in solution. So now the same thing is written in a you know pretty well, this is Harvard's representation, and this is the actual cyclic 6-membered ring system. It is a cyclohexane kind of a ring system. And in this ring system, you see the OH in an alpha glucose is in the axial position. In beta D glucose, it is in the equatorial position. So when you observe the beta D glucose, all the bulky groups are in the equatorial position. That is why beta D glucose is a stabler form of glucose. And that is the reason why in solution it is 63%, whereas alpha D glucose is only 37%. And the importance of these two forms of glucose and what kind of polysaccharides they form, or which kind of polysaccharides contains these different forms of glucose, are all presented in our earlier videos. Please, you can refer to them to get a detailed understanding about this. So now coming to the acetal formation. So like I told you, this is hemiacetal because one alcohol moiety is added by nucleophilic addition reaction. And the second alcohol group can, if you are taking excess of alcohol, the second alcoholic group can react with this hemiacetal and undergo nucleophilic substitution reaction. So the OH group is substituted by OR minus to form acetal. So this is the most significant property of aldehydes and ketones. So when it is forming an acetal, this is also one of the ways in which you can protect a functional group. So if you want to protect a OH group, you can convert it into an ether, or it is also called as a acetal. So in this particular case, we see the hemiacetal is having one hydrogen at least, one OH group at least. Whereas in acetal, both the oxygens are, masked by some other group. There is no hydrogen in them. So now let us go back to the carbohydrates. So in the monosaccharides, like say for example here, we see that alpha D glucose is having the anomeric carbon, and this anomeric carbon is having an OH group, and this is a hemiacetal. So all monosaccharides in cyclic systems are hemiacetals, and they will have OH group in the anomeric carbon. Now, when these two monosaccharide react to form a disaccharide, the reaction can happen at the first OH group and the fourth OH group, and it can condense and removal of water, and it can form a glycosidic linkage. This is actually an ether linkage, but then this is called in carbohydrate chemistry, we call this as a glycosidic linkage. So in this case, the interaction is between the OH of the first carbon with the OH of the fourth carbon. But it need not be like this. It can also be with 1 and 1. But we are talking about the disaccharide maltose, which is occurring in nature. And this maltose seem to have a glycosidic linkage between the first carbon of one glucose and the fourth carbon of another glucose. So this is called as 1,4 glycosidic linkage. And in this carbohydrate, the disaccharide, we see this particular OH group on the first carbon. This is actually the anomeric carbon of this particular glucose. And this OH group is not reacted upon, and it is free. So this is a hemiacetal, whereas this is an acetal. Why? Because the OH group is now converted into an OR group. So there is an OR here and then OR here. So that is why this particular glycosidic linkage is actually a acetal group, and this OH group is a hemiacetal group. So let us see this particular molecule and you will be able to understand. So this is shown in a proper way, wherein you have two cyclohexane kind of a ring systems, and we have this OH group which is in the equatorial position, is reacted upon with the fourth carbon. So this is the first carbon. Okay, so this is the first carbon, the second carbon, the third carbon, the fourth and the fifth, and the sixth carbon. So what we see here, the interaction is between the first and the third carbon. Actually, it must have been with the fourth. So in this particular case, it is between the first carbon and the third carbon. So it is 1,3 glycosidic linkage. And so this glycosidic linkage is also called as a acetal, because this OH is replaced by OR group, and this OH is replaced by OR group. And here this OH is free. So whenever you see in a molecule, in a disaccharides, yeah, or trisaccharides, in small carbohydrate molecules, you carbohydrate, that is when we are talking about polymeric molecules, uh, you will see glycosidic linkages between the individual monosaccharide units, and you will also see the end moiety wherein the OH group will be free, could be free. So what we have to look for is whether there is an acetal or a glycosidic linkage. Is the glycosidic linkage formed between the anomeric carbon or not? So that is what we must see. So because only the anomeric carbon will have a newly formed OH group. Not all other carbons can open, and that is, the molecule cannot break at any other position other than these positions. The positions marked in red and blue are the places where the molecule can break. There are no other positions in the molecule where the molecule can break into an open chain. So again, this is another carbohydrate, which is a disaccharide, which is sucrose. Sucrose is nothing but our table sugar, the sugar that we use in our coffees and teas. So this is actually made of alpha D glucose and beta D fructose units. Again, what kind of linkage is it? So what we see here is the first carbon's OH is bonded to the second carbon's OH. So the linkage is, or interaction is, between the first OH and this OH. And then condensation has happened, water is removed, and then this forms a glycosidic linkage because this is the anomeric carbon. So this 2 carbon is the anomeric carbon of fructose, and 1 carbon is the anomeric carbon of glucose. So what we see in case of sucrose is the OH groups that are present, or hemiacetal groups, the OH that is present in both the carbohydrates, are interacted upon and water is removed and they form a acetal. This linkage is called as 1,2 alpha, 1 alpha 2 beta glycosidic linkage. But what we must remember, only if the OH group is available, the molecule can mutarotate, or it can open into an open chain in solution. In the sense, sucrose will not open up in solution when we dissolve it in water. So that is why sucrose is called as a non-reducing sugar. So any sugar that can open up in solution or it can mutarotate is called as a reducing sugars, and those sugars which cannot mutarotate are called as non-reducing sugars because they do not undergo reaction. Again, detailed explanation about reducing and non-reducing sugars are in our earlier videos. You can see those videos and benefit from them. So now let us see some of the sucrose molecules and, sorry, some of the disaccharide molecules, and then observe their structures. So these are examples of sucrose, lactose, and maltose. And when you, this is like an exercise for us. All I want you to see is how to locate the anomeric carbon. So for that, first you see the oxygen which is there in the ring system, the oxygen and the CH2OH group that is outside the ring. So we know this oxygen is there. So the carbon next to the OH, sorry, oxygen will be the anomeric carbon. So in this case, this is the anomeric carbon. Similarly, in the CH2, in fructose, as I told you, one side it is hydrogen, the other side only is the OH group. So this is the anomeric carbon. So in case of sucrose, you see there is a glycosidic linkage that has formed between the two anomeric carbons or the two hemiacetals. So this molecule by itself cannot mutarotate. Why? Because it doesn't have the hemiacetal structure. Both the OH groups have been involved in condensation and they are removed. So there is no possibility. Here it is only hydrogen. So sucrose cannot mutarotate. And when sucrose is breaking down, it forms a 6-membered ring sugar, and this is a 5-membered ring sugar. Both of them are different. This is glucose, this is fructose. Now coming to lactose, again what you see is two 6-membered ring systems, but then they are different molecules. Again, in this particular molecule, all I want you to see is the anomeric carbon. Here, this is the anomeric carbon because this oxygen carbon next to the oxygen. And in case of lactose, you see this is the anomeric carbon. That is the OH group which is free. This is the anomeric carbon. And the reaction has happened at the 1, 2, 3, 4 on the fourth OH group. So this interaction is 1, 4. And so the OH of the first carbon is free. So this molecule can open into its, this hemiacetal can break into an open chain. So this lactose molecule is actually a reducing sugar because the OH is open. Whereas here, this is not, it is locked in position. And so reaction, this ring will not open, but the other part of the ring will open, and that will favor further reactions. Similarly, let us see maltose. Again, in case of maltose, you see this particular position. This is the anomeric carbon, and the anomeric carbon's OH is free. So again, this molecule can open and it can undergo mutarotation. So the understanding about mutarotation is carbohydrates can equilibrate between open chain structure and the ring structure, and this is because of the formation of the hemiacetal group, and this hemiacetal can always open into a aldehyde or ketone as desired if it is not involved in any other reaction. So now let us see the question. So in this particular question, as I told you for the sucrose molecule, see here in this case, this particular position is the anomeric position. So this OH is removed, and so glycosidic is formed. So this OH, this carbohydrate cannot open, or this part of the molecule is not available for ring opening. Whereas when you see the second carbohydrate, again in the second carbohydrate, this particular place is also this first, that is the first carbon, okay, or the anomeric carbon. So in this particular structure, what we see is both are anomeric carbons, and both the anomeric carbons are involved in the formation of the glycosidic linkage. So this particular molecule will not show mutarotation because there is no possibility of the molecule to open up into the open chain because the hemiacetal groups have been removed and acetal has been formed. So now going to the next molecule. In the next molecule, what we see, this particular carbohydrate's OH is locked, whereas this OH is free. So we know this molecule can mutarotate. So now next, let us see the next molecule. So the third molecule, again third molecules, this carbohydrate is locked. So this can also mutarotate because this OH is free. It is in the form of a hemiacetal. Now let us go to the last case, wherein what we see here is again this is the anomeric carbon, and this is also the anomeric carbon. So this is an anomeric carbon, this is an anomeric carbon, and because this is CH2, and so this side it is only hydrogen. So this molecule cannot mutarotate. So we know that A cannot A and D cannot mutarotate. C and D can C and B can mutarotate. So C and B are ruled out. So now the question is between A and D, who is the what is the which one is the answer? So for that they have given the second case. They will give two different. So it's very clear. It's a very simple question. Just now we saw it is sucrose. One part is fructose, another part is glucose. So the answer is D. And this is two glucose molecules together. So this is the correct answer. So among the four options that are provided to us, what we see here, mutarotation is not possible in A and D on hydrolysis will give two different carbohydrates. So the answer for this particular question is D. I hope you understood. D, please subscribe and share it with your friends so that they will be benefited. Thank you.